Good afternoon, students. Welcome to yet another lecture of the Advanced Green Manufacturing Systems course under the MOOCs program, and I am Dr. Deepak Philip from IIT Kanpur, and this course is aimed towards many of our masters, final year undergraduate students, practitioners and all who are interested in making or realizing sustainable green manufacturing systems. And how can we realize those advanced systems, and what are the tools and techniques that are required to do that or realize that is what is part of this course is about. And I am Dr. Deepak Philip and I am from IIT Kanpur. And also today's lecture we are getting into is the concept of what we call as modeling, the second part of the modeling course. Earlier, if you remember, we have already covered basics of modeling, basics of optimization, and then we covered modeling, okay, using binary variable, which is a 0-1 system. We already covered that. Then we also looked at the rules of thumb or guidelines of modeling, okay, and in that guideline I have told about keep it continuous, right? I mean, guideline 4 was about keep it continuous, and today what we are going to do is how do we model with continuous variables. Okay, today's lecture is all about using continuous variables. For modeling. How do we do that? That is the fundamental question, and what we will do is we will work through an example. So let's take another example today, okay, and it is always better to work through an example because once you do an example it actually makes life easy. So what we are going to discuss today is a fertilizer factory. Okay, a fertilizer factory is planning to produce biofertilizer. Okay, the aim is to produce biofertilizer bags of 50 kilograms. So the content of the bag is 50 kilograms. Okay, 50 kilograms of biofertilizer containing between 0.5 and 1.25% of carbon. 0.5% to 1.25% of carbon. Carbon is denoted by the letter C, and 0.3% to 0.5% nitrogen. Nitrogen is denoted by letter N, and no more than 0.05% sulfur, and sulfur is denoted by letter S, and no more than 0.04% phosphorus. Okay, phosphorus is denoted by letter PH. So when you say between 0.5 and 5%, that means it is 0.5% to 1.25%. That's what we are talking about. In this case, this is an interval. When we say no more than 0.05%, that means it is 0 to 0.05%, because the values below, okay, values below 0% do not make sense in this problem. Okay. So what we are saying here is, if we say 0%, that means sulfur is not at all present. Okay, so 0 doesn't mean that it's present. 0 means absolutely is the absence of one thing. Okay, and there are 7 raw materials. So ideally there are 7 raw materials available to produce the fertilizer. Okay, so there are 7 raw materials available from which the biofertilizer can be produced, whose composition availability is in kilogram and cost is in rupees is given below. Okay, so there are 7 raw materials. So the raw materials are given in this table. So these are the 7 raw materials: 1, 2, 3, 4, 5, 6 and 7. So the 7 raw materials are limestone, pyrite, worm meal, bone meal, neem cake, groundnut cake and charcoal. Okay, and the limestone, the first raw material limestone, has 3% of carbon in it, 0% of nitrogen, this means absence of nitrogen, 0.013% of sulfur, 0.015% percentage of phosphorus, and 40 kilograms of limestone is available and at a cost of rupees 200. Okay, so it's 200 per kilogram. You can think about it that way. This is cost per kilogram. Okay, so then the pyrite is the second raw material available, which has 2.5% of carbon, 0% of nitrogen, the nitrogen is absent, 0.008% of sulfur, 0.001% of phosphorus, 30 kilograms is available at 250 rupees per kilogram, like that. Then worm meal has no carbon, 0% of carbon, 0% of nitrogen, 0.011% of sulfur, 0.05% of phosphorus, and 60 kilograms of it is available and it's at 150 rupees per kilogram. Same way, then there is bone meal, 1.2% of carbon, 0% nitrogen, or nitrogen is absent, 0.002% of sulfur, 0.008% of phosphorus, and 50 kilograms of it is available at 220 rupees per kilogram. Neem cake has 0% carbon, 90% of nitrogen, 0.004% of sulfur, 0.002% of phosphorus, 20 kilograms of it is available and the cost is 300 rupees per kilogram. Then groundnut cake, same way, 0% carbon, which means absence of carbon, 96% of nitrogen, 0.012% of sulfur, 0.003% of phosphorus, 30 kilograms of it is available at 310 rupees per kilogram. And then final raw material is charcoal with 90% carbon, 0% nitrogen, 0.002% sulfur, 0.01% of phosphorus, 25 kilograms is available at 165 rupees a kilogram. So the aim is pick from the 7 raw materials a combination, okay, or by itself. Either use a option so that you get it by itself, or you use a scenario where a combination is being picked up. Okay. So the problem setting, I hope you guys understand that we are going to produce biofertilizer bags of 50 kilogram weight containing 0.5% to 1.25% of carbon, 0.03% to 0.05% of nitrogen, 0.05%, no more than 0.05% of sulfur, and no more than 0.04% of phosphorus. And there are 7 raw materials using which you can produce a fertilizer, and their composition, availability and cost is given, and we already discussed the details of it. Right. So now the manufacturer's aim, what does the manufacturer want? Okay, or what we are looking at is what is the aim of the problem, or what is the aim of this optimization. This is the aim of the optimization problem. So the most important question we have is what is the aim of the manufacturer, or what does the manufacturer want to do? Okay, we can say that the manufacturer wants to determine. So what does he want to determine? Determine the least cost combination. The least cost combination of raw materials. So you want to find the least cost combination of raw materials. Why? That it can use to produce what? The fertilizer, the biofertilizer, that can be sold. So the manufacturer wants to produce biofertilizer. Okay, so biofertilizer, we are saying biofertilizer in bags of 50 kilogram each. Okay, so each bag is 50 kilogram. and he wants to produce this biofertilizer that can be sold. It can be sold to the customer. And how do the manufacturer wants to produce this biofertilizer? The how is by determining the least cost combination of raw materials, okay, or how he want to produce it is by combining the raw materials. How many raw materials are there? 7 of them. Okay, by combining the raw materials to achieve least cost while meeting the criteria. Okay, you want to do the least cost while meeting the criteria. What are the criteria? Okay, what are the criteria? Okay, the first criteria, the criteria is already mentioned here. These are the criteria, the carbon and nitrogen and sulfur and phosphorus. So if you think about it, the criteria are, okay, 0.5% to 1.25% of carbon, then 0.3% to 0.5% of nitrogen, okay, then no more than 0.05% sulfur, which means 0% to 0.05% of sulfur, and no more than 0.04% of phosphorus. So 0% to 0.04% of pH. Okay. So your biofertilizer should satisfy this criteria. Should satisfy. Okay. And while satisfying this criteria, you want to do this, you combine them with the raw materials in one fashion or another, combining the raw materials, okay, to achieve least cost. Okay, you get the least cost while meeting this particular criteria of carbon, nitrogen, sulfur and phosphorus. So this is the aim of the manufacturer as far as we are concerned. Okay. So remember, then the next major thing, or not the next major thing, the first major thing for us is choosing the variable. In the stepwise process of what we called as the optimization, the first thing is about choosing the variable. So we say that we choose the variable by determining, we choose the variable. Why would we choose the variable? By determining which components of the problem can be changed, to create different possibilities or different options. So what we are trying to find out here is which are those components of the problem that can be changed, or we can adjust those wins so that we get different options or different possibilities out of this. Okay. So here the manufacturer can change the raw materials. Manufacturer can change the amount of raw materials. And how many raw materials are there? 7 of them. Okay. The raw materials used to produce the fertilizer. Okay. The manufacturer can change the amount of raw materials. He can change the amount of raw materials. There are 7 of them. Okay, to produce the fertilizer. Okay, and by changing the amount of raw materials, okay, a different variable can be used to represent the amount of each raw material or the quantity of each raw material. of each raw material. So since the manufacturer, all he can do is he can change the amount or quantity of the raw material. When we say amount, we are also thinking about quantity, okay, quantity of the raw material, so that the fertilizer can be produced. We can use a variable to represent the quantity of the raw materials. So the variables will be, let's say we define the first variable as x1, okay, which denotes the kilograms of limestone, okay. Your variable x2 denotes the kilograms of pyrite, okay. x3, third variable, denotes the kilograms of worm meal, x4, the kilograms of, we will have bone meal, okay. So this is your raw material 1, okay. This is your raw material 2, raw material 3, raw material 4, okay. So these are the rows of the table, ideally speaking. x5 will be your kilograms of neem cake, okay, raw material 5, x6 kilograms of groundnut cake, okay, raw material 6, then x7, okay, is kilograms of charcoal, okay, so your raw material 7, okay. Even though I wrote it like this, ideally the variables are to be little x, okay. So this x is equal to, so use lowercase, okay. All right. So what we are saying that, please note that these variables can reasonably assume a continuum of real values, okay. So unlike discrete values of previous problem, so the quantities, you can think that the values, these x1, x2, x3 all the way to x7 can take are values between 0 to, so you can say that, so in the case of x1 for the limestone, okay, it can vary between different values. We will write that in the next constraint, ideally speaking. So we can write that down, okay. But ideally speaking, that these values can take, these variables can take continuum, a continual values of real, continuous set of real values or continuum of real values, unlike the previous case where it was 0 and 1, okay, kind of a scenario. So all these variables, okay, these are our what we call as, we are going to, this is going to decide what will be the cost of the fertilizer or the biofertilizer that we are trying to manufacture at the end. Now we get into the second part of it. Once we identified what the variable is, we now get into what we call as modeling constraints, okay. So first thing is, variables of this problem are naturally bounded below by 0, okay. So what we are saying is that, which implies lowest possible value of x1, x2 all the way to x7 is 0, okay, or we are saying is that negative amounts don't make sense. When we say minus 3 gram or minus 3 kilograms of something, it actually does not make any sense in this. Okay, and variables, second aspect. Okay, so this is the first aspect. The variables are bounded above by their availability. Okay, so how much is available, which means highest possible value E of x1, x2, etc., x7 is their individual max availability. So how many kilograms of individually they are available, okay, are the maximum value. Okay, or you cannot use a particular raw material more than what you have. So what does this mean? This means that if you have 30 kilograms of something, then the max you can use is 30 kilograms, or you cannot use a particular raw material more than what you have. Okay, so whatever is the quantity you have, that's the upper limit of this. So we now have the lower bound, or the lowest possible value of the raw material of the variable, and we also have the highest possible value of the variable. So if that's the case, then we can write the constraint as for x1, then constraints on the variable can be written as, okay, so for variable x1 it is 0 less than or equal to x1 less than or equal to what is the upper value. So for that we go back to the table and we find that for 1 the upper limit is 40. So we go back and write 0 less than or equal to 40. So this is for the case of limestone. Okay, so the minimum you can use is 0, the maximum you can is 40, because 40 is the maximum kilograms of limestone that is available to you. Similarly for the second one, 0 less than or equal to x2 less than or equal to what is that value? We go back to the table and that value turns out to be 30. So we come back and say 30, and 30 is meant for the pyrite. Okay, and then the third variable x3 is less than or equal to, think about it, it is 60 kilograms, so it's upper bounded by 60. Okay, so I'm just going to, then that is worm meal. Okay, so you get the upper limit from the worm meal row of the table. The fourth variable 0 less than or equal to x4 less than or equal to, that you go back again to the table, and the fourth one bone meal, you can see that the value possible is 50. So we go back and we write it as 50, that is for bone meal, right? Bone meal. Okay, then for the fifth one we write it as 0 less than or equal to x5 less than or equal to, because it's 0, because negative values does not make any sense, the lower bound is 0, you cannot have negative values of this. So we go back to the table again and we find that the neem cake, which is the fifth one, is 20. So we go back and we write it as 20 and we say it is neem cake. Okay, then the sixth variable x6, the quantity of the next raw material, we go back to the table again and we say it's groundnut cake, limit is 30. So we come back and say it is 30 for the groundnut cake. And the last variable 0 less than, X7 less than or equal to the quantity. We go back again and look at the table as charcoal, it's 25. So we come back and write it as 25. That is charcoal. Okay. So now we know that the individual variables, okay, all individual variables, what is the values. So for limestone, this is the lower bound. So this is the, we call it as the lower limit or lowest possible value of the variable. We cannot take a value less than 0, and this is the higher limit or highest possible value. Okay, of the variable. So between this, okay, can take any value between these limits. Okay. So what we are saying here is that each variable has a lower limit and a higher limit. Okay. So which means the highest possible value it can take. Between these limits, the variable can take any value, okay, between these limits. So that's why it's a continuous value. Okay. Can take for example, X7 can take any value between 0 and 25. So it can be 0.325 or 1.67 or 3 or 9.893, whatever it is. You can put whatever values that for any of these 7 possible variables. Okay. Then we talk about the second set of modeling constraints. So the first constraint is we talked about is what about the how we can model the or how the individual variables are bounded in this. Now we can say that, now we say let's assume that any amount of raw material contributes to the same amount of fertilizer, Okay. So for example, what we mean by this is 30 kilogram of charcoal plus 20 kilogram of bone meal. If we do that, we should be able to get 50 kilogram of fertilizer. Okay. If we take 20 kilogram of pyrite plus 15 kilogram of worm meal, then we will get is 35 kilogram of fertilizer. Okay. Fertilizer means the composition of the other requirements might vary, but the quantity, okay, whatever you have the quantity, the same amount, any amount of raw material will give you the same amount of fertilizer. So if you use this many kilograms, it will give you exactly the same kilogram. These will match. Okay. This is what we assume. Okay. Also, we know that we need to produce, we also know that we need to produce at least 50 kilograms of fertilizer. Okay. We have to at least produce 50 kilograms of fertilizer to make it into one bag of this. Okay. So we also know that we need to produce at least 50 kilograms of the fertilizer. Then if this is true, then what we have is, we can say x1 plus x2 plus x3 plus x4 plus x5 plus s6 plus x7, all of them together should be greater than or equal to 50. So what are we saying here is, in the previous cases x1, x2, x3, x4, x5 up to x7 were the quantities, okay, these are the quantities of the raw materials, quantities of raw materials, okay. If that is true, and we have an assumption that the quantity, any quantity of the raw materials that we take, we sum them up together, same amount of fertilizer we will also get. If that's the case, if we sum all these 7 raw material quantities put together, we should be able to get 50 or more kilograms of biofertilizer, okay. So, but notice that we do not assume that we will produce exactly 50 tons. Okay. You should notice that we don't assume that we will produce exactly 50 tons. This is not just equal to 0, it is greater than or equal to 0. Okay. Why? Why don't we assume that? Because it may be necessary to produce more to meet other requirements of the problem. So let's say we only make exactly 50 kilograms, okay. So what, let's say, let's think about it pictorially, okay. So here is a small bag, okay. It's a small bag of x1, okay. There is another bag of x3, okay. The third bag of, okay, x4, like this, okay. We combine all of these, we should be able to get a bag of fertilizer. It will be 50 kg, okay. These will be individual values, okay. So these plus this, these 3 together should give you 50 kg of this. But what we are saying is, let's say there is a scenario that if we make only exactly 50 kilograms and some 1 kilogram is lost at the time of packaging, then you will only end up with 49 kilograms. So it is necessary for us to produce slightly more to meet other requirements of the problem whenever they come up. So usually that's the reason why we write this constraint in a fashion like this, that we will produce more equal to or more than 50 kilograms, okay. Hopefully that makes sense to you guys, okay. Now if that is true, then we are getting into the third aspect of modeling the constraints of this problem. So the other constraining feature of this problem is that the biofertilizer must contain certain percentages of carbon, nitrogen, sulfur and phosphorus. So what we are saying here is, we already talked about the constraints of the variables and the total quantity constraint, we already put it in. But another constraining aspect of this problem is that the end result biofertilizer must contain certain percentages of carbon, nitrogen, sulfur and phosphorus. This is also a requirement of this. You cannot just mix and match. Okay, so this implies that you cannot just pick any 50 kg. Okay, instead choose the combination such that the percentage requirements of carbon, nitrogen, sulfur and phosphorus is satisfied. So you cannot just pick up any 50, okay? Just don't pick up any 50. Instead, choose the combination such that the percentage requirements of these 4 are satisfied. Okay. So now then translate, we have to translate the composition requirements, now we have to translate the composition requirements into constraints on our variable. Constraints on our variables. What are our variables? x1, x2, x3, x4, x5, etc. Okay. So the variables are x1, x2, x3 all the way to x7. These are our 7 variables. So the composition requirements that we have of carbon, nitrogen, sulfur and phosphorus need to be put into constraints on the variables. Okay. So what we do is, let's first focus on the 0.5 percentage to 1.25 percentage carbon composition. Okay. So first we are going to focus on the carbon composition constraint. Then the other composition constraints. Then the other composition constraints can be modeled similarly. Okay. So once we attack the carbon composition constraint, then the other composition constraints we can use the same methodology to model them. From the given data, we know the percent contribution of carbon by each of the raw materials. So we can say that if we go back to the previous table, we know the percentage composition of carbon. Okay, this gives you the percentage composition of carbon contribution from all these raw materials. Okay, so if I write it down, then I can write it as 0.03. So it's 3% is translated to 0.03 times x1 plus 0.025 x2, right, plus 0 times x3 plus 0.012 times x4 plus 0 x times x5 plus 0 times x6 plus 0.9 times x7. Okay, I can write it this way. So where do I get these? This comes from the table. The 3% is equal to 0.03. This is 0.025. This is 0, 0.012, 0, and 90% is 0.9. Right? You are dividing it by 100. So if we follow that, then we can say that we can write a constraint like this, and you can see that, okay, this one 0 times this variable is 0, this is also 0, this is also 0. So then we can further rewrite as 0.03 x1 plus 0.025 x2 plus 0.012 x4 plus 0.9 x7. Okay. So this will be the constraint, because these variables are all zeros, because their coefficient is also 0. So you see x1, x2, x4 and x5. So to achieve the carbon, okay, or carbon composition can be achieved by raw materials 1, 2, 4 and 7. Okay. So what we are saying here is, using these stuff, these of the any of these 4 raw materials, we can achieve the carbon composition, right? All right. So from this equation, which is this equation is this, right? From this equation, okay, we can easily calculate the amount of carbon, for any choice of variables. Okay. So whatever the variables we choose, from there we can calculate the amount of carbon, whatever be the choice of the variables. Okay. So, but it's not very simple, it's not completed yet, because we also know that the requirement involves the percentage of carbon in the fertilizer. The percentage of carbon in the fertilizer. Okay. So our requirement is on the percentage of carbon in the fertilizer. It's not about the quantity of the carbon, but it is the percentage of the carbon. Okay. So we have to divide the amount of, carbon by the amount of fertilizer. To obtain the percentage. So what we are saying here is that we have to divide the amount of carbon, whatever the amount of carbon. Where do we get the amount of carbon? We get the amount of carbon we obtain from here. This is the amount of carbon. Okay. This amount of carbon has to be divided by the amount of fertilizer and multiplied by 100, so that we can obtain the percentage. Okay. So we can say percentage of carbon, okay, is equal to 100 multiplied by kilograms of carbon divided by kilograms of fertilizers. Okay. So if you do this, then this ratio will give us the percentage, and we know that the percentage of carbon has to be between, this has to be between 0.5% to 1.25%. So now we can put this can put a constraint on this, because we know what the constraint is. Okay. So what does this implies to? This is equivalent to saying it is multiplied by 100 multiplied by our previous equation, which is 0.03 x1 plus 0.025 x2 plus 0.012 x4 plus 0.9 x7. This is the amount of carbon divided by, okay, what are we dividing it by? X1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7. This below is the total amount of fertilizer, right? So this one is the amount of carbon, this is the amount of carbon, and as we said, this is the amount of fertilizer, right? Amount of fertilizer. Okay. So if that is the case, what we can do is, so now we know that this is a percentage, and which can be further simplified by multiplying the 100 into the numerator. Okay. So if you multiply 100 into the numerator, we simplify, which will be equal to 3.0 x1 plus 2.5 x2 plus 1.2 x4 plus 90 x7 divided by x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7. So this equation is the percentage of carbon in the fertilizer. Now we know that using this equation, the requirement that the fertilizer must contain between 0.5 percentage to 1.25 percentage of carbon translates into, so how can we write that? We can write it as 0.5, this is the because this is also in percentage, less than or equal to 3.0 x1 plus 2.5 x2 plus 1.2 x4 plus 90 x7 divided by x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7. So this is the percentage of carbon less than or equal to 1.25. Okay. So these are all in percentages now. Okay. So this constraint, this now enforces the carbon content percentage constraint. Okay. So by looking into this approach, we can see now we have a constraint that tells you how the carbon content percentage can be easily modeled. So thank you very much for your patient listening. Continue reading and hope to see you soon in the coming aspects of this course. Thank you very much.